రెండు రెండు ప్రోగ్రాంలు రెండిట్లో లీవ్ ఉన్నాయి, ఇది ఉన్న ఇంకొకటి దాంట్లో లేదు. నేను అవి లేకుండా పిల్లలు ఇస్తాను సైలెంట్లో పెట్టుకొని దేని నేను ప్రణాళిక దిక్కుతాను.
Okay. All right. Welcome everyone to the second day. So today we continue with the concept of qubits. Okay. Yesterday we saw how to model bits, correct? Today we will see how to model qubits. All right. So for qubits, what we do is, again, for one qubit, we will model it as a vector. Yeah, yesterday we modeled one bit as a vector. So we will model it as a vector alpha beta. But yesterday the numbers a comma b were non-negative real numbers. Now it will be complex numbers. Complex numbers. So alpha beta are coming from C, the set of complex numbers. And yesterday we had that the probability vector had L1 norm 1. Now we will have this vector has L2 norm 1. L2 norm 1. So what is L2 norm? L2 norm of this vector is L2 norm square is mod alpha square plus mod beta square, which should be 1. Mod alpha square plus mod beta square, not just mod alpha plus mod beta. Mod alpha square plus mod beta square, that is L2 norm square. Yes. It is L2. So this is the L2 norm and this is square. L2 norm square. Okay. So now what is a complex number? A complex number alpha is written as a plus ib, where a is real number, b is real number, I is imaginary. Imaginary I. Please raise hands who are familiar with complex numbers. Very good. Because we will be using complex numbers throughout the course. What is it? I is square root of minus 1, right? Square root of minus 1, that is I. One can easily see that there is no real number which can form square root of minus 1, right? Any real number square has to be non-negative. So if you are taking square root of negative numbers, then you get into imaginary numbers. And you can combine imaginary numbers plus real numbers to get complex numbers. So you have A, B in R. Mod alpha, what is mod alpha? If you have alpha which is A plus IB, then mod alpha is square root of, see, A and B now are real numbers. So square root of A square plus B square, that is mod of alpha, which is a complex number. So mod of alpha is a real number, in fact a non-negative real number. Alpha is a complex number, but mod alpha is a non-negative real number. Okay, for a complex number alpha, we define what is known as conjugate of that. Alpha star, conjugate of alpha. What is conjugate of alpha? A minus IB. If it is A plus IB, it is A minus IB. Okay, that is conjugate. Good. Now let us take examples of qubit vectors. Example of qubit vectors. One example is 1 over square root 2 minus 1 over square root 2. Okay. what is the mod of, so alpha, what is alpha here? What is beta? What is mod alpha square? 1/2. What is mod beta square? 1/2. Total adding up to here 1, 0. What is alpha here? Beta. So we can see it is also mod alpha square plus mod beta square adding to here. What is alpha? What is beta? 4i/5. Okay. So what is, now let us do carefully, okay. Mod alpha square is how much? Yes. Now mod 4i/5 square. You see, mod 4i/5 square. Remember, mod is always going to be a non-negative number. Correct. So, the mod of 4i/5 by this definition, this is a complex number, right? 4i/5. By this definition, in 4i/5, what is the a there? 0. And what is the b there? 4/5. So you get mod alpha as square root of 4/5 square, which is just 4/5. So mod here is just 4/5. Square is square. Now what is it here? 9 plus 16, 25 divided by 25, that is 1. So all the time we will have this. Even we have complex numbers as part of the elements of the vector, but our mod square addition which forms the L2 norm square of that vector V is always going to be 1. Okay. So this is one thing. Any questions here? Hey, this one is just saying that mod of 3/5 will be, you express 3/5 in this a plus ib form, 4i/5 in this a plus ib form. Now remember, yesterday we mentioned that going from classical to quantum, our gate set will also increase. Will now include unitary matrices. Yesterday we saw that our operations are captured by stochastic matrices. Today we will see our operations are captured by unitary matrices. Okay. Okay. Right. So let us say U is a unitary matrix. Okay. V is a vector alpha beta. When the operation happens, view that as, like yesterday, the matrix multiplied to the vector U times V. We get the new vector W. Now L2 norm, okay, this is the L2 norm anyway. So remember we were saying L2 norm square was mod alpha square plus mod beta. So just L2 norm is square root of mod alpha square plus mod beta square. So this U now, remember yesterday stochastic matrices were L1 norm preserving. L1 norm preserving. Here now L2 norm preserving. See, I told you this whole difference between L1 and L2. Now L2 norm preserving. That is, if V, whatever is the norm of V, will be also the norm of W2 norm. So these 4 conditions, 1, 2, 3, 4, are actually all equivalent. One implies the other. Okay. These are the 4 properties of unitary matrices. However, they are all equivalent. One implies the other. L2 norm preserving, invertible, U dagger U equal to U dagger equal to I. We will see what is U dagger. Orthonormal columns, orthonormal rows. We'll see what it means. Okay. U is our matrix. Let us say U is this 2 by 2 matrix represented by U00, U01, U10, U11. When we have a matrix U like that, we say U transpose. For a matrix we can define transpose. Transpose is you have U00, this U10 goes here. So this first column becomes the first row. Second column becomes the second row. You see this? Transpose. Columns becomes rows. First column, first row, second column, second row. Transpose. Then conjugate. You conjugate, you star. You basically do entry wise star. Every entry is a complex number. Every entry you do star. Remember what we said conjugate of a complex number? A plus IB becomes A minus IB. So every entry you do conjugate. That is U star. Agreed? Now there is something called as U dagger. This is also called U dagger, also U conjugate transpose. That means you do both the operations. You do conjugate also, you do transpose also. U dagger is, so this is U transpose, U conjugate transpose. So you can see if you can do conjugate transpose, this will become all star star, and still it is like this here. You did U transpose here and you did all the stars. You come here. Agreed? U transpose, then you do star. All entries are star. You come here. Agreed? Any questions? Yes? No. What I am saying is, V can be any vector. U is a unitary matrix. U is a unitary matrix. U is a matrix. It's a 2 by 2 matrix. V is a vector. V is a 2 by 1 vector. W is a 2 by 1 vector. Column vector. V is a column vector. W is a column vector. U is a unitary matrix. Yes, so unitary matrix satisfy these 4 properties. 1, 2, 3, 4. What are the properties? L2 norm preserving, invertible, that is U dagger times U. So we just saw what is U dagger, right? Property is, if you multiply U dagger with U, that is the same as, see for matrices, if you multiply, see for numbers, if you multiply A times B, that is the same as B times A. Agreed? So they commute, what is called as commuting. A times B is the same as B times A. However, for matrices, if I have a matrix A and matrix B, if I multiply A times B, it need not be the same as B times A. They need not commute. Okay, multiplication need not commute for matrices. However, in this case, for a unitary matrix U, that's why we are writing it as U, U for unitary. Unitary matrix U, U dagger times U is the same as U times U dagger is the same as identity matrix. What is the identity matrix? Remember yesterday we saw it's a matrix with ones on the diagonals and zeros elsewhere. That is the identity matrix. Ones on the diagonals, zeros elsewhere. Agreed? U dagger U equal to U, U dagger equal to identity. That is invertibility. It's called invertible. Matrix is invertible. And the inverse of that matrix U is U dagger. The inverse of U dagger is U. A matrix A has an inverse B if A times B is the same as B times A, the same as identity. That is why this matrix is called invertible. You do the operation, then you can reverse it. Because identity means what? Nothing has happened, right? So you do U followed by U dagger, you come back to nothing has happened. It's called invertible. Now, normal. Okay, orthonormal columns. What does it mean, orthonormal columns? Look at the columns here. Okay, this one, this one. Firstly, orthonormal means two things: orthogonal, pairwise orthogonal, normal. That's why it's called orthonormal. Normal means, you look at this column U00, U10, this column, its norm, the L2 norm will be 1. L2 norm of that first column will be 1. Similarly, the L2 norm of the second column will be 1. Every column will have norm, L2 norm 1. Agreed? That is what we say, columns are all normalized. They all norm has 1. Agreed? Remember, our columns in the stochastic matrix, the L1 norm was 1, right? They were all adding up to 1. Here the L2 norm is 1. Look at the correspondence, always L1 and L2 correspond. Orthogonal. What does orthogonal means? Means these two columns, their inner product, we will see what inner product means. Their inner product is 0. Huh? -1, somebody said -1? No. Okay, inner product is 0. What is inner product? We will see what is inner product. Inner product of U0, that is U0 dagger times U1 is 0. U0 dagger times U1 is 0. Yes, very good observation. Very good observation. So in this case, actually, we can see that this 3 already implies 4. So that's the nice thing that happens. You impose this constraint, then it already implies the other constraint. Also, here we are putting this orthogonality constraint, which was also not there in stochastic. There only the normalization constraint was there, but the orthogonalization constraint was not there. Here we are putting that also. Okay. But you see, if you impose just the constraint number 1, it will already imply constraint number 2, 3, 4. If you impose any one of them, it will imply the other 3. They are all equivalent. Okay. Now, you see, okay, we were going to look what is the inner product. Okay. So let's say I have two vectors, column vectors V and W, and we want to define what is their inner product. Inner product is defined as V dagger. Remember V dagger. It is the same operation. Okay. What are we going to do? What was V when we do dagger of a matrix? What did we do? Conjugate transpose. So let us first do transpose. Column vector transpose is row vector, right? Remember we said we will replace the column by rows. Then we will conjugate each entry. So V0 V1 becomes V0 star V1 star row. Agreed? That is V dagger. W, if you have, similarly W dagger. Inner product of V and W is V dagger times W. V dagger is a row now. A row can be multiplied to a column, right? 1 cross n, n cross 1. You can multiply. So a row multiplied with a column, what will happen? Okay, we are multiplying this with this, right? So V0 dagger with W0 plus V1, sorry, V0 star with W0 plus V1 star with W1. Agreed? This is it. Now that becomes a scalar. By scalar I mean a number. Here will be complex number. But V dagger W is a scalar. V is a column vector, W is a column vector. The inner product, which is V dagger W, is a scalar. Similarly, you can define W dagger V, right? W dagger is this times V. If you do W star, W0 star V0 plus W1 star V1. But you can see that V1 dagger W is not necessarily V dagger, sorry, V dagger W is not necessarily W dagger V. You have to be careful there, again, non-commuting issue. But you can see one thing, that this is actually the star of this. If you do a star of this, you get this. That's another thing that will happen. Okay? Conjugate. Because now it's a complex number, you do its conjugate, you will get the other one. Okay? Okay. This we see now. Any questions about what is the inner product? What is the unitary matrix? Yes? Sorry, what's your question? Excuse me, Mr. Subbareddy, because it is getting recorded, do you want the questions to be recorded as well? Do you want the mic to be given to them so that it's there? Up to you, I am saying. Better? There's the mic.
Hello.
Yes?
Sir, you have shown that scalar it is, scalar matrix.
Yes.
How can we say it is scalar or vector, something like that, sir?
What is a scalar, what is a
Yes,
vector?
Sir, yes, sir. We don't know about matrices, how we consider scalar.
No, you see, if you take a row vector, row, and multiply with a column, remember, for a matrix, if you multiply an n cross m matrix with a m cross k matrix, you get n cross k. Agree? Row vector is 1 cross n, row. Agreed? Multiply with column n cross 1. What do you get?
1 cross 1.
What is 1 cross 1?
So you mean single row is considered as scalar, sir? Single number.
This is scalar. 1 cross 1.
Yes.
Okay? If it is 1 cross 1, it is simply a number. Could be complex number, but that is what we call scalar. Scalar is simply a number.
Okay.
Okay? Okay. Any more questions? Okay, let us look at some examples of unitary matrices. Okay. This Hardeman matrix, okay, we are going to use this Hardeman matrix a lot, okay. Hardeman matrix. Okay, Hardeman matrix. This matrix is 1 over square root 2, 1 over square root 2, 1 over square root 2 minus 1 over square root 2. This entry, this fourth entry has a minus there, and this is going to make a whole lot of difference, this minus. This is where the power of the Hardeman matrix will come. The NOT matrix we already saw before, 0, 1, 1, 0. Identity matrix 1, 0, 0, 1. Rotation matrix cos theta minus sin theta, sin theta cos theta. Okay. What is the L2 norm of this column? 1. Agreed? What is the L2 norm of this column? What is the inner product of the two columns? 0. Agreed? Anybody has any question about that? Yes. Why it is 0 you are asking? Huh?
Actually, it is a already predefined matrix, sir. Is there any reason to take 1 by root 2 value, and why the value of fourth one is minus? Is there any reason, sir? Like identity matrix, it is predefined.
No. See, these are different types of unitary matrices.
Okay.
Identity, rotation matrix.
We cannot change that value. The value is fixed for that matrix, sir. Like 1 by root 2, 1 by root 2. We have to take that only.
That only. Okay. So, we saw the inner product is norm is 1, L2 norm is 1, inner product is for the two columns. What is the inner product of the two rows? One over square root 2 times 1 over square root 2, half, plus 1 over square root 2 minus times minus 1 over square root 2, minus half, half minus half, 0. So inner product of the rows is 0, inner product of the columns is 0, both the rows are norm 1, L2 norm 1, both the columns are L2 norm 1. And you can check that H times H dagger is identity. What is H dagger? Transpose conjugate, but what will it turn out to be? Same as H. You see this? More difference, because it is all real entries, so conjugate won't make a difference. Transpose also making no difference here. It is same as H. So H times H is identity. Hardeman is its own inverse. Okay. For the NOT matrix, you can verify all the properties are there. Identity matrix, all the properties are there. What about this matrix? What is the norm of the first column? L2 norm. Why is like that? Trigonometric identity. Sin square theta plus cos square theta is 1. You see? Now, you see, now it is not one matrix, it's a class of matrices. For every theta, you will get another matrix. It's a class of matrices. But the point is, every matrix in this class is a unitary matrix. It satisfies all the desired property. Norm is 1, norm is 1. Inner product, what is the inner product of the two columns? Cos theta times sin, minus sin theta, plus sin theta times cos theta. Inner product of the two rows, 0. Okay. What is the dagger of this? Cos theta, sin theta, minus theta, cos theta. the sign, the minus goes here. Agreed? So these are examples of unitary matrices. Any questions so far? Very good question. You will see, later we will see that it will rotate a vector by an angle theta. When we will view a qubit as a vector in the two-dimensional plane, we will see that it rotates by angle theta. That's why it's called rotation matrix. No, Hadamard matrix is only 2 by 2, but later we will see how we are going to do tensor of matrices. Like we can do Hadamard tensor Hadamard. That will be 4 by 4. We will see Hadamard, I mean we will see tensor of matrices for larger systems, multi-qubit systems. Here we are only talking about one qubit system. Okay. There is another generalization of Hadamard matrices called the Fourier transform. Okay, that we will also see later on. Okay. This is the inner product V and W. The inner product is V dagger W. No, inner product of V with W is V dagger W. Inner product of W with V is W dagger V. These are two different things. The order matters. Order matters. Okay. Okay. Any question? Good? All right. So we go to the next one. Okay. Let us look at what is now a measurement. Remember yesterday we said, okay, we toss a coin, it is like this, maybe we model it as 1/4, 3/4, probability 1/4 head, probability 3/4 tail, then we see it, it becomes either head or tail, right? That operation of seeing the coin, the analogous operation here is measurement. The qubit is there, then we see the qubit, we measure what it is. So when we measure, let's say there is a qubit state alpha beta. We measure it. What happens? With probability mod alpha square, the outcome becomes 0. But remember 0 was represented as 1, 0. So with probability mod alpha square, the outcome becomes 1, 0. With probability beta mod beta square, the outcome becomes 0, 1. Agreed? And one thing you see, why is this forming a probability? Because remember we said mod alpha square plus mod beta square is 1. And mod will always be a non-negative number. So as such, mod alpha square and mod beta square form a probability vector. Got it? So whenever we are measuring a qubit alpha beta, it collapses. The word uses collapse. It collapses to 0 with probability mod alpha square, collapses to 1 with probability mod beta square. Measurement. Okay. Any questions? That is measurement. Example. Now, let us say I have this vector v, qubit v, 1 over square root 2, 1 over square root 2, v1, 1 over square root 2, minus 1 over square root 2. If I measure v0, what will I get? I will get 0 with what probability? 1 by 2, agreed? I will get 1 with what probability? If I measure v1, I will get 0 with what probability? 1 with what probability? So you see, if I just measure v0, I am getting 0 and 1 with probability half-half. Even v1 I am measuring, I am getting 0 and 1 with probability half-half. So just measuring them is not helping to distinguish them, because both cases it is half-half. If I look at it, I get 0 with probability half, 1 with probability half, 1 with 0 with probability. I cannot distinguish them. How to distinguish? Because they are different qubits, right? You see, v0 and v1, there is a minus here. So as such, their states are different. In fact, they are orthogonal. You can see the inner product is 0. These are two orthogonal states. That means they are far apart, okay? They are distinguishable. But if we just measure in the computer, this is called as measurement in the computational basis. This measurement, because these two, we call them as computational basis, 0 and 1. Computational basis. So somebody was asking me, how do we model superposition, right? So now we can see. You see, alpha beta. I can write alpha beta as alpha times 1 0 plus beta times 0 1. Agreed? Alpha beta is alpha times 1 0 plus beta times 0 1. Agreed? Yes or no? So this is one. See, now what are we doing? We are working in this two-dimensional vector space. Agreed? We are talking about vectors 2 cross 1. Therefore, we are working in two-dimensional vector space. These two form a basis for the vector space. What does basis means? Basis means every vector in the vector space can be written as some linear combination of these basis states. In fact, they form a orthogonal basis state. Why? Because the inner product of this and this is, what is the inner product of this and this? Whenever the inner product is 0, we say they are orthogonal. Okay? So inner product of these two basis states, which we are calling 0 and 1. Remember, we are calling this 0, right? Later you will see that we represent this as ket 0, like this. We represent this as ket 1. We are calling them 0 and 1, right? We represent as ket 0, ket 1. Okay, this bracket notation. So now, these are the two orthogonal basis states, which we call as computational basis. Computational basis. And this linear combination is what we call superposition. Superposition of basis states. Okay? Whenever there are completely distinguishable basis states, orthogonal, distinguishable, therefore their linear combination will be called superposition. Agreed? This is, and now we can sort of map it to the, remember the electron picture we were talking about. Electron can be in orbit 1, orbit 2, orbit 3 and all that. These are distinguishable states. Like if you measure the electron, it will fall to either orbit 1 or orbit 2 or orbit 3. Correct? It won't fall to like orbit 1.75. Agreed? Either orbit 1 or orbit. If you look at the position of a particle, if you look at the position will be either here or here or here. Right? These are completely distinguishable states. But electron can be as such in a superposition, that is a linear combination of those basis states, which are completely distinguishable basis states. That is called a superposition. Any system, if it can be in some number of distinguishable basis states, then it can also be in a linear combination. But now the linear combination we are considering is in the complex vector space. Our field now is complex. We are doing linear combination with respect to complex numbers. Agreed? Okay. So concept of superposition is clear. Good. Now we are trying to see how we can distinguish these two vectors. Remember, these are orthogonal vectors. So orthogonal vectors we should be able to distinguish. But if we just measure as such, we will not distinguish them. So what we can do is, we can do some unity transformation first on these vectors and then try to distinguish. Agreed? So let us do a Hadamard transformation on this vector. Okay? Hadamard transformation on this vector. So let's do that. Okay, maybe let's make this also interactive. Okay, who would like to volunteer to come and do this? Just we have to multiply the Hadamard transform with this vector. Please, anybody can volunteer? Yes. H times V0. H, okay, let's write H first. H equal to 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2. Okay? Now let's multiply. You can also do that. Take 1 over square root 2 outside and then you can do 1, 1, 1, 1, 1 minus 1. Yes. Okay? For a V0 also you can take out 1 over square root 2 out if you want. Yes. Now you multiply. H times V0. What is that? No. You can take you can multiply the scalars separately. You see, you have these numbers outside, right? You multiply them separately. A matrix you multiply separately. That will simplify calculation. You see this? Correct? See the calculation? Maybe you can explain to them. Explain to them. Yes. Somebody at the mic, no? No, the other mic. battery is not. Okay. Yes. Yeah. Can you? Yeah, please do that. Explain.
Okay, here we are doing matrix multiplication H into V naught. So scalars we can multiply outside, and here we have first row into this column, which will be 1 into 1 plus 1 into 1. So we have 2, and 1 into 1 plus 1 into minus 1 will be 1 minus 1, which will give us 0. And this is scaled by half. So each element will be scaled by half. So first element scaled by half will be 1, and second 0 scaled by half will be 0.
Yes. 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 Agreed. Okay, now what is H times V1? You can erase the left part and you can write there. Okay, very good. Yes.
Okay. Here we will have 1 into 1 plus 1 into minus 1. 1 into 1 plus 1 into minus 1. So first element will be 0. And next we have 1 into 1 plus minus 1 into minus 1. So this will be plus 1 again. So this will be 0 and this will be 2. And we have those scalars outside 1 by root 2 and 1 by root 2 here. So 1 by 2 times 0, 2. Like previous case, we can scale both the elements and we get simplified 0, 1.
Is it clear? Any question? Please ask if you have any question. Clear? So we see now, thank you very much. So we can see now that, you see, if we multiply H times V0, we get 1 comma 0, H times V1, you can 0 comma 1 now, 0 1, 1 0 0 1. Now they are very different, correct? Now you go ahead and measure, what happens? This is 0 already. That means you will get 0 with probability 1. Now this one you will get 1 with probability 1. So now they are very different. Earlier we were doing it was half both the cases. Now after the Hadamard transformation, it is 0 with probability 1, 1 with probability 1. Correct? Very different. So this is the way we can now distinguish. Orthogonal states can be distinguished. We just have to apply.
It was in superposition state. Once we measured, it collapsed in one state. Is that?
Yes. It collapses to one of the computational basis states. Okay.
You have discussed some formal proof. So is there any formal proof that if we apply this Hadamard transformation, then we will get either like something with probability 1 or 0? Like initially we were getting.
No, it will not always be the Hadamard transformation, but it is true. And we'll do a formal proof, I believe, in one of the weekly assignments, that if you have orthogonal states, you can always do some unitary transformation and then distinguish them with probability 1. Okay? Yes?
You have written measurement there, so by doing this Hadamard we are actually getting one of the two states. So I have a similar question, like is it always that it will so by applying Hadamard are we doing the measurement?
No,
In
we are
this case, yes, and other cases maybe no. Is it
no, we are first applying the Hadamard and then doing the measurement. We are first applying the Hadamard transformation and then doing the measurement in the computational basis. Sorry, what was your question?
Sir, by applying Hadamard we get 0 and 1.
Yes.
So it is like measurement in this case.
No, not like measurement.
Then it is measurement. No.
Okay, okay. I understand what you're saying now. What you're saying is, oh, we were doing measurement, so we were getting 0 and 1. Now here also we are getting 0 and 1, which is fine. The point is, once you have got 0 and 1, remember, okay, it's like this. Suppose I had this electron, okay, which was in the superposition of orbit 1 and orbit 2. I did a transformation on it. It then reached either orbit 1 or orbit 2. Let's call orbit 1 as 0, orbit 2 as 1. It reached there. But once it reached there, I still have to look at it.
Okay, we have not still looked at it.
I still not looked at that electron. It has gone to orbit 1. It was in superposition. Now I did a transformation and gone to orbit 1 or orbit 2. Very good. But I still didn't look at it, no? So that process of looking at it involves a certain interaction of that system with some apparatus, right?
So will it change when we look at it?
No.
No.
If it is in the computational basis state, it will not change because we are doing the measurement in the computational basis.
Okay.
So if it is already in orbit 1 or orbit 2, and we look at it, it will be in orbit 1 or orbit 2.
Okay. But not always, like measurement may lead to change in state.
May lead to changes. For example, suppose we looked at it when it was like this.
Okay.
Suppose it was in the superposition of orbit 1 and orbit 2 and we looked at it. Then what will happen? It will go into one of the orbits, 1 or 2. It will no longer be in superposition. So that time its state will change. That time the measurement will change its state. But if it is already in orbit 1 or orbit 2, then we are measuring, it won't change the state.
So here we are applying Hadamard gate full stop, and measurement we have not done yet.
Yes.
Sir, here we are using Hadamard on 1 by root 2 and 1 by root 2, and we are getting 1 and 0 as result. If I apply another Hadamard gate to this result, I am going back to the original
Exactly. Exactly.
vector.
You are perfectly all right. Why? Because remember what we said, Hadamard is its own inverse. That is, you apply Hadamard followed by another Hadamard, you get identity. That means you do 2 times Hadamard, you have not done anything. That means you go back from 1 over square root 2, 1 over square root 2, back to 1 over square root 2.
So even number of Hadamard gate will get me to the original
Exactly.
vector.
Exactly. That is correct. Anybody else? Any questions?
when we are doing some measurement, it collapses either 0 or 1.
Correct.
So I'm expecting 1, for example, but it collapses to 0.
Okay.
Then how?
It's okay. It can happen. If, for example, in the classical case also we said, right, I toss a coin. Suppose it's a fair coin. Probability half head, probability half tail. I keep it like that, I don't show it to you. Now it is probability half head, probability half tail. Maybe you are expecting a head. I show you it is tail. Can happen, right? Maybe you are expecting head, but I show you it is tail. It can happen.
Any effect is there on the solution?
Huh?
For example, any effect is there on the solution? I'm expecting.
Yes, exactly. So that is where the design of the algorithm comes into picture. We have to design the algorithm in such a manner that our result always turns out to be as desired. That is where the novelty in design of the algorithm is. That is, we are always able to maneuver the state towards where we want it to go. That is where the design of the algorithm comes in. Yes.
If you're going to the physics, then we can measure the energy, position, all those things, right? So here we are just talking about one type of measurement. So like if we have to measure energy, do we have to like convert it into this basis? Like it's a very complicated thing, which I am asking maybe for most of the people, but like I had this doubt, like
Yes, indeed. So, for example, you could be measuring position or you could be measuring momentum, correct?
Yeah.
But in order to make a position measurement, you have to do a different transformation followed by measurement in the computational basis to do position measurement. If you want to do momentum measurement, you have to do a different transformation followed by measurement.
Okay. So depending on the quantity, we have to do the.
Exactly. Depending on your observable, you have to do a different transformation and then measure. Correct? Any other question? That is why the uncertainty principle comes in, right? Because these are sort of measurements in what they call mutually unbiased basis, which therefore you cannot measure both of them at the same time with high accuracy. That is where the uncertainty principle, uncertainty between position and momentum comes in. Yes, they are not. They are in what they are called as mutually unbiased basis, position and momentum basis. Okay, any other question?
So like how do you physically represent a Hardeman matrix? Like for example, when you were speaking about classical circuits, there were some circuits, right? So like that, how do you actually make a circuit type of thing in this?
No, so then here circuit not a problem. We can draw a gate. I call it Hardeman. Yeah, sure. So circuit we will see anyway. So circuit wise, like on paper or on board, circuit wise is not a problem. If you are asking how do we do it actually in the lab, right? How do we do the transformation, Hardeman transformation in the lab? Then what happens is, that time they will, I think physicists can answer it better. Huh? The thing is, they'll shine some lasers, etc. on the system and achieve those transformations.
So when you say that you are applying Hardeman gate without looking at it, and then you're looking at it, right?
Yes.
So how do you actually apply Hardeman gate without looking at it?
So yeah, that is possible. So that's amazing, but that's possible. So they do that, they shine some lasers, etc., and they achieve the transformation. I mean, I don't know all the details of it because, experimental physicists can answer this much better. But I'm just saying that that's what they seek to achieve in the lab. Huh? Observables are, yeah, denoted by O. That's true. So yeah, so this is all very interesting. How they actually manage to achieve it in the lab. Very interesting. Decoherence, yes. Decoherence is where a system like this, okay, even if you are not doing anything to it, automatically it will get measured because the environment will interact with it. Correct? You have left the system, right? But still it is interacting with the environment all the time. Even they try to put the system in a very, very, very cold temperature, right? Very, very close to very, very small Kelvin. So that it is in that cold temperature, they are hoping that it doesn't interact much with the environment. Even then it interacts. And because of its interaction, the environment measures it. You are not trying to measure. You are not doing any apparatus on it to try to measure. But the environment measures it. And that is, therefore it collapses to either 0 or 1. That is what is called as a decoherence. When the system interacts with the environment in a manner that collapses it, is called decoherence. Okay? Any further questions? Any further questions? Good. All right. Then we move to the next thing. Next thing is what we are referring to as multiple bits. Okay? Multiple bits. So all the time till now we are talking about 1 bit or 1 qubit, correct? Here suppose we have 2 bits. Then the 2 bits 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 possibilities for the 2 bits. Agreed? If I have 2 coins, head, tail, 4 possibilities. I can represent it by a 4 by 1 vector now. 4 by 1 vector. Because I can write the probabilities of all the 4 possible states. Let us say 1 over 8, half, 0, 3 over 8. Again what will happen? If this is a probability vector, all the values will be non-negative. They will add up to, are they adding up to 1 here? Now, if I have such a system, I now have a 4 cross 1 matrix. 4 cross 1 matrix, correct? A column vector with 4 values. Stochastic matrix example, now I have 4 by 4 matrix, right? Earlier we had 2 by 2 matrix, now we have a 4 by 4 matrix. Example is this, let us say one example of a stochastic matrix. But properties remain the same as we said before. All entries are non-negative. Of course zeros can be there, huh? Because when we say non-negative, doesn't mean they have to be positive. They can be zeros, can be there. Zeros can be there, but columns are adding up to 1. Columns are adding up to 1. Agreed? I think somewhere somebody was asking, can we have entries other than 0 and 1, right? You see, it has entries which is other than zeros and 1s. You can have entries other than zeros, 1. However, columns are adding up to. Agreed? Now multiple bits, now we have multiple qubits. 2 qubit system. 2 qubit system we are representing as a 4 cross 1 vector. Column vector with 4 entries. But now we have to have what property? L2 norm should be 1. Example 1 over square root 2, 0, half, minus half. What is the L2 norm square here? This thing square, half, 0, half square, 1/4, minus half square, 1/4. Total addition, 1. So L2 norm will always be 1. That is the property. Unitary. So this is a 2 qubit system, okay? It's a 2 qubit system. Unitary. Unitary transformation will be now 4 by 4. Example, this one. This is called as a control knot unitary. Control knot. Okay? It acts on a 2 qubit system. If the first qubit is 0, it does nothing on the second qubit. If the first qubit is 1, it does a knot on the second qubit. That's why it's called control knot. Control knot. It's given by this matrix here. We can see now all the columns are norm 1, L2 norm 1. All the rows are L2 norm 1. Columns are orthogonal. Take any 2 columns, the inner product is any 2 columns. First and third, second and fourth, first and second, everything, 1 and 4, everything. Any pair of columns, inner product is, any pair of rows, inner product is orthonormal rows, orthonormal columns.
Can we say every permutation matrix is C not K?
Yes, correct. Every permutation matrix is a unitary matrix.
It's not involuntary matrix.
Huh?
But it may not be involuntary matrix.
It may not be
Involuntary matrix.
involuntary. What is involuntary? Huh?
Square of that matrix is I.
Square of the matrix is?
Identity.
Oh, square of the matrix is identity. No, not the square. U times U dagger is identity. U times U dagger, not the square. Okay, any questions here? Yes. Actually, we may need one help, right? Each time passing on the mic.
Sir, so you said it's a control knot. This is 1, 1, and then in the third row, last one, and in the last row, third is 1. So why is it a control knot? I didn't understand.
Oh, why is this a control knot? We will see this, okay? I just mentioned it, but we will see this. It's kind of like, you see, here is an identity, okay? This 2 by 2 block here is identity.
Okay.
So this is doing nothing. This 2 by 2 block is a knot, correct? So in a sense, if you think about it, later when we will see it in the circuit picture, it will become clear to you that when the first qubit is 0, it does nothing. That represents this 2 by 2 block. If the first qubit is 1, it flips the second qubit. That operation will become clear, okay, when we'll see it in the circuit picture. But yeah. Excuse me, are you also attending this course? Huh? Oh, but it's not good actually. If you are attending the course and if you have to keep doing this, huh? Because it will change your focus, something. Maybe we should have somebody else who, yeah.
A little off topic.
Huh? We'll try somebody else. Yes, that's okay. We can do it later, sir. We do it later. It's okay. Yeah.
A little off topic, but what is a permutation matrix, sir?
Okay. She took us off topic. Permutation matrix, for example, this is a permutation matrix. A permutation matrix is a matrix of only zeros and ones. Every column has a unique one, every row has a unique one. You see, every column has a unique one. You can see that? Only one and every other entry is 0. Every row has a unique one. That is called as a permutation matrix. It is in a sense doing permutation of strings. This string goes there, this string goes there, this string goes there, like that. It's a permutation of strings. So, it is actually in a sense, you can call it a classical unitary transformation. In a sense. Okay? A classical operation which is a unitary transformation. For example, okay, one thing you can note. This is also a stochastic matrix. Yeah? What? Doubly stochastic. Yeah, even doubly stochastic. Stochastic, you can see it as stochastic matrix. It's a stochastic matrix, it's also a unitary matrix. Agree? It's a stochastic matrix. It's also a unitary matrix. In fact, as she remarked, it's doubly stochastic, meaning even the rows are adding up to 1. Stochastic, only the columns are adding up to 1. Here the rows are also adding up to 1. Huh? Life? Yeah, this one.
It's a line diagram.
Line?
Line diagram. If I plot in a graph, so it get a
Line diagram.
graph, sir.
Okay. Okay. So permutation matrix is the one where every column has a unique one, every row has a unique one. Okay. Okay. Now let us get to the concept of tensor products. Okay. It's a very important concept for us to consider the multi-qubit systems. Okay. Multi-qubit systems. Suppose I have one qubit system V, 2 by 3, 1 by 3. No, sorry, this is not I just described to you tensor product here. This is not normalized, okay? But I am just describing what is a tensor product of two vectors. Okay, so I have, in fact, they are L1 normalized, right? They are L1 normalized. So now suppose I have V and W like that. Tensor product is what? Again, note that the tensor product is also not commutative necessarily. So V tensor W is not necessarily W tensor V. Okay. What is V tensor W? I take V, I take W. First I multiply 2 by 3 with 1 by 4. Then 2 by 3 with 3 by 4. Okay. Then I multiply 1 by 3 with 1 by 4. 1 by 3 with 3 by 4. You see now? 2 by 3 is the first entry here. I multiply with both the entries of W. Then the second entry 1 by 3 multiply with both the entries of W. That is a tensor product. Now you just see, I am just writing all the multiplications here. That's all I am doing. Okay? Agreed? Clear what is tensor product? This is also known as AKA. AKA means also known as Kronecker product. Yes. The mic for her.
The tensor product is always of two column matrices.
No.
Then
We are
it
just
can
going to
be
get
n
it.
cross n.
No, we're just going to get into the more general tensor product here. Okay. Tensor product can be done for any two matrices. Any two matrices. For example, suppose I have this matrix A and B. For now, they are 2 by 2 matrices. Okay. What do? I take the first entry here, multiply with B. A11 times B. What is A11 times B? A11 times B11, A11 times B12, A11 times B21, A11 times B22. Agreed? Yeah. Same size as B. A11 times B, A11 is a scalar, B is a matrix. A11 times B is this matrix here. Every entry of B. One second. So, first let us note the following. We have a matrix A, matrix B, correct? Just see what is a scalar times a matrix. First let us see that. Scalar times a matrix. What is a scalar times a matrix? A scalar times matrix B, you simply multiply that scalar to all entries of B. Agreed? Scalar times a matrix is clear? Okay. Then what do? If you do A tensor B, you take A11, multiply with B. This is a 2 by 2 matrix. A12 multiply with B. This is a 2 by 2 matrix, 2 by 2 matrix, 2 by 2 matrix. So 4 by 4 matrix. Right? 2 by 2, 2 by 2, 2 by 2, 2 by 2. Correct? This will be a 4 by 4 matrix. B tensor A will be what? Now you see, you will take B11 times A. Here you are taking A11 times B, you take B11 times A. Then B12 times A, B21 times A, B22 times A. So you can see the order matters. Huh? But this is also be 4 by 4 matrix. For example, if generally this is a, let us say n by n matrix, this is m by m matrix or k by k matrix, then this is nk times nk matrix. Nk times nk matrix. Agreed?
Sir, can tensor product be of only square matrices?
No.
No.
You see, this operation does not restrict it in any manner. Even if, for example, this was a column, A was just a column matrix, B was a square matrix, I can still multiply. There is no problem. I can still do the tensor operation, right? Because this tensor operation is not restricting me in any manner, like how the multiplication was restricting me, right? I needed the number of rows to be equal to the number of columns. Here there is no restriction. Yes. Any dimension can be done tensor product with any dimension. It is different from matrix multiplication. Agreed? You can see it is different from matrix. It's not the same as A times B. It is represented by A tensor B. Kronecker product. Tensor product. Agreed? Any other questions? Okay, good. This is tensor product. Okay, now let us look at some properties of tensor product. Okay, many of these properties will be coming very helpful for us. Associative. A tensor B bracket tensor C is the same as A tensor bracket B tensor C is the same as A tensor B tensor C. What does it mean? It means that suppose I do A tensor B first. Okay, I have three matrices A, B, C. I do A tensor B first. Then I tensor with C. Bracket means the operation means first you have to do A tensor B. Remember, in our bracket, this one bracket always takes the precedence, right? So bracket we'll do first inside. Suppose I do this first, then I do the second one, tensor. It is the same as first I tensor B and C, then I tensor A from the left. You see? First I tensor A and B, then I tensor C from the right is the same as first I tensor B and C, then I tensor A from the left. Agreed? Agreed? So therefore, because wherever we put the bracket doesn't matter, we just remove the bracket. Correct? A tensor, B tensor, C, it is clear. The order of the operation doesn't matter. First you tensor A, B, then you tensor C from the right, or you first tensor B and C, then you tensor A from the left, doesn't matter. You are going to get the same things. That is why it is called as the associative property. Associative property. Like for example, if you are multiplying three numbers, A, B, C. First I multiply A, B, then I multiply C, or I multiply B, C, then I multiply A, doesn't matter. Agreed? No, that matters. Just now we saw, right, A tensor B is not the same as B tensor A. Need not be the same. Okay? Order matters. That matters. Now there is a property called, this is going to be a very useful property, okay? A tensor B multiplied with, see, whenever we are not writing here anything, just writing bracket, it means multiplication. Simply multiplication, regular matrix multiplication. A tensor B multiplied with C tensor D. A tensor B multiplied with C tensor D is the same as A multiplied with C tensor B multiplied with D. You see this? A tensor B, C tensor D. A and C will join together, B and D will join together.
Sir, what if the dimensions don't match? How will we multiply A and C?
Yes, in this case dimensions have to match. In this case, dimensions have to match.
Otherwise, this will not match.
See, firstly, even to have this multiplication, the dimension of this big matrix must match the dimension of this big matrix.
Yes.
Correct? Agreed?
So A is say 2 by 2. B is 2 by 2.
Yes,
And C is 2 by 3. Then it is possible.
possible.
But what will be the case when this will not hold? What will be the dimensions when this will not be able to be applied?
No, for this to be applied, the dimensions must match.
Yes.
Yes,
So suppose my A is 3 by 3
yes.
and 3 by 2
Hmm.
and B is 2 by 2
A is 3 by 2, B is 2 by 2, okay.
and C is something 4 by 2.
Then it won't match.
It won't match.
Then you can't, I don't know whether the kind of numbers you are giving, whether you can even define this product. Because for this,
You had said that tensor product, any matrix can do tensor.
yes, this will be not a problem.
Yes.
This will be not a problem, but this product will be a problem. This product should be well defined. Look, this big matrix dimensions, the number of rows here must match the number of columns of this big matrix. Only then this product will be well defined. You agree? Matrix product, always you have to match the dimensions for the matrix product to be defined. Tensor product is okay, but matrix product, the dimensions must match. Huh? No, you should be able to multiply A and C. Number of rows of A must match the number of columns of C. A and C must be compatible, B and D must be compatible. Any questions? Any questions? Okay. So this, and now let us go to the distributive over addition, this property. What is that? A tensor B plus C is A tensor B plus A tensor B plus A tensor. Similarly, you can do distributive from the left side. A plus B tensor C is A tensor C plus B tensor C. This is like multiplication also. You see, A times B plus C is A times E plus A times C. Correct? Multiplication also distributes over addition. Similarly, here it distributes. Scalars float freely. That is, alpha is a scalar. It is a complex number. Alpha times A. If you first multiply alpha to A, remember we saw how to multiply A scalar to a matrix. You simply multiply that number to all the entries of the matrix. Alpha times A you do first, then you do tensor B. It's the same as you do A tensor alpha times B. It is the same as alpha comes out A tensor B. So it's a scalar. You can put scalar with A or B or outside. That is what we call scalars float freely. Agreed? Same. No. Scalar is the same as complex number. Scalar, by scalar we simply mean complex number. Number. Whichever field it is. So if we are working in complex field, it is complex number. Yes. Scalar. Like how he did, right? He took the 1 over square root 2 out. That is the scalar, he has taken it out. Okay, good. So these are properties of the tensor product that we are going to use. Okay. Now let's get to the concept of independent random variables. Independent random variables, correlated random variables. Okay, you see, if I have a W1 which is A comma B, W2 which is C comma D, I can have V which is W1 tensor W2. Okay. Now, when I can express V as tensor product of two vectors W1 and W2, then I would like to call it as an independent system. Now, for example, let us look at this V here, half 0 0 half. Can I write this vector as a tensor product of two vectors? Can I write it? Yes or no? This vector half 0 0 half, can I write it as a tensor product of two vectors? Yes? Who is saying yes? Yes. How do you say that? Can you please pass the mic to him? No, just pass the mic to him. Who has the mic?
The respective element of W1 is being multiplied with the respective column of the W2, right? A with C, A with D.
Correct.
And again, B with C and B with D.
Agreed. Yes. So, suppose this was a tensor, okay? Then we are writing this, correct?
Yeah.
But now this has to be equal to this. Is it possible? Can I have values A, B, C, D such that this is the same as this? Can I have such values? Huh? Not possible. Why not possible? Maybe you pass the mic to her.
AD is equal to 0, no? So
A,
if A
yes.
is equal to 0,
Ah.
how can we say that AC is equal to half?
Correct. No, but AD equal to 0, either A is 0 or D is 0.
Right.
Correct? So you are right. So either A has to be 0 or D has to be 0. But if A is 0, then AC is 0. But then this is half. But if D is 0, then BD is 0. But then this is half. So either way it cannot work. So therefore it is not possible. We cannot have this vector represented like this. So therefore we cannot write it as a tensor product. Once we say we cannot write it as a tensor product, then it is not independent. That is, it is correlated. This one is now a correlated system. If you can write it as tensor product, it is independent system. If you cannot write it as tensor product, it is a correlated system. Okay. Now, entanglement, concept of entanglement, same thing. For this, if you have, here we were talking about the probability vectors. Here we are talking about the qubit systems. 1 over square root 2, 0, 0, 1 over square root 2. Can I write it as W1 tensor W2? Huh? No. What is the reason? What is the reason? Same reason. Agreed? If I have AC is 1 over square root 2, either A has, sorry, if AD is 0, either A has to be 0, even for complex number, doesn't matter. If AD is 0, either A has to be 0 or D has to be 0. That property holds even for complex number. You cannot take two non-zero complex numbers and make a 0. Cannot. Okay? So, if AD is 0, then this is either A is 0 or D is 0. With A is 0, then AC is 0. Therefore, this is cannot be. If D is 0, then BD is 0. Cannot be. So again, it is not a possible to write it as a tensor. Therefore, what we call it as a entangled system. In a quantum system, 2-qubit quantum system, there can be two types of correlations. One correlation is kind of a classical correlations, which is here, for example. This is called as a classical correlation. So accordingly, even in quantum systems, you can have classical correlations. But there are other kinds of correlations called as entanglement. You might have heard the word entanglement. This is an entangled system. Okay? Ah, then it's okay. Then I think it is okay, right? Yes, agreed. If you take 0, 0, half, you are saying, right? Then I think it is a tensor of 0, 1 with 1, 1, something like that. Correct? Yeah. Okay. Agreed? So this is the concept of, so here it is when we say independent system means you can write it as a W1 tensor, W2. Okay, now we can get into the so-called Dirac notation, the Ketbra notation, okay? Dirac notation. So Dirac, this is named after Paul Dirac, a very famous physicist. He came up with a very compact notation to describe all these, because now once we have 1 qubit system, 2 qubit system, 10 qubit system, like that, suddenly all these vectors and matrices, they start to grow a lot, very big. So he came up with a compact way of representing these vectors and matrices, called as the Dirac notation. I had actually mentioned here, ket, this is called ket 0. Ket 0 is 1 0. Ket 0, 1 0. Ket 1 is 0 1. Ket 1. They form a basis for C2, that is two-dimensional vector space over complex numbers. C2. Right? They form a basis. We can see that. Every vector in C2 can be expressed as a linear combination of these two vectors, when the linear combination is taken over complex scalars. For example, if I want to write this 1 over square root 2 ket 0 plus 1 over square root 2 ket 1, that is 1 over square root 2 1 0 plus 1 over square root 2 0 1, that is the same as 1 over square root 2 1 1. When we add vectors, we just simply add them entry wise. Okay, addition of vectors is simply entry wise. 1 plus 0 is 1, 0 plus 1 is 1. Now 0 0, ket 0 0 is the same as ket 0 ket 0. But whenever we are saying, you see, you look, whenever you have two matrices, suppose we are writing them next to each other and the dimensions don't match, then the only operation that makes sense is tensor product. So these are both are column vectors. We are writing column vectors next to each other. Only operation that makes sense is tensor product. So for brevity, we will often skip writing this tensor product. We'll just write ket 0 followed by ket 0. Even for further brevity, we will just write as ket 0 0. But it actually represents this, which actually represents this, which actually represents this. 1 0 tensor 1 0, which is 1 0 0 0. Agreed? Yes? Please pass the mic to him. Behind.
So what if dimension matches? Then how do we know that it will?
Yes, so then we have to be careful in specifying whether we are doing a product or a tensor.
Okay.
If the dimensions are matching. If the dimensions are matching, we have to be careful. Okay.
Careful in what sense? I mean, careful in what sense? I mean,
we have to write that symbol.
Okay.
We have to explicitly write the tensor symbol there. 2 qubit. Agreed. Yes.
You can directly go from 0, like ket 0 0 to 1 0 0. Why do you need to do that?
No. What do you mean you can directly go from here to here?
Because it's a 2 qubit system.
Yes.
So it has to be 1 0 0 0.
No, I agree. But what, for example, let us see. Let us see how we write 0 1. So you can see that there is this mapping here. You see, 0 1 is ket 0 tensor ket 1, which is 1 0 tensor 0 1. What is this? See here, when we are doing 1 0 tensor 1 0, what was happening? 1 followed by 1 1, 1 followed by 0 0, 0 with 0, everything 0. 1 with 0 1 you will get just 0 1, and 0 with 0 1 will get 0 0. So 0 0, you can see when we are writing 0 0, we are getting this vector with 1 in the first place.
Okay, so if I want to generalize to n bits, this will be useful for me?
Yes.
So if I take 3 bits, then ket 0 0 0, I can use this formula and reach to what it will be?
Exactly. So you can see 0, 1, you are getting 1 in the second place. 1, 0, you will get 1 in the 1, 1, you will get 1 in the. So you can see that first place, if you write the first place is actually the 0th place. Designate the first place actually as the 0th place. Then the second place as the first place. So 0, 1, 2, 3. Then you can see that the binary notation of 0 is what? 0, 0. Binary notation of 1 is what? 0. Binary notation of 1 is 0. Binary notation of 2 is 1, 0. Binary notation of 3 is 1, 1. So you can see the ket 1, 1, the 1 will be exactly in the location that corresponds to what 1, 1 is the binary location of. You see, this is the mapping, which is what you were pointing at. This is the mapping. If I write any string, 0, 1, 1, 0, 0, whatever, whatever, it corresponds to what? One big vector where everything is 0, 1 is in which location? Whatever this string is the binary encoding of. Agreed? Right. So, here. So we saw we can write 1, 0 and 1, 1. Okay. Now suppose I have this 1, 2, 3, 4, 5, 6 zeros and 6 ones. I have this vector here. I write like this compactly. What does it mean? It means 1 over square root 2. This one, this all is means 1 is in the, and all this means 1 is in the 63rd location. Why 63rd? Because 1, 2, 3, 4, 5, 6. 2 to the power 6. How much is 2 to the power 6? 64. But we are writing from 0. So it will be 63rd. Agreed? So this, instead of writing this whole big vector, we can write compactly like this. Especially if the vector has almost everything is 0, just a few ones. Then this is a much more compact way of writing that vector. This is called as the Dirac notation. Okay, introduced by Paul Dirac. Now, same thing we can generalize. Suppose I have any n qubit system now. We will generalize now. N qubit system. N qubit system, the basis would be any string x in zeros and ones with n zeros and ones. 0, 1 to the n means it's a string of n bits of zeros and ones. X is a string of n bits of zeros and ones. They will now ket x there. Now we can see, right, if we have any string, we know what is ket x means by our notation. This will form a basis for C 2 to the n. 2 to the n dimension, because now see, if I have any string 0, 1 to the n, how many strings are there? 2 to the power n. 2 to the power n strings are there. So now they are forming a basis for a 2 to the power n dimensional vector space. Using complex entries. So see 2 to the power n. The dimension is 2 to the power n. Now I have such a vector, say ket phi. It is a superposition. Now all of this will be called as computational basis states. All of these 2 to the n basis states will be called computational basis states. So I have a superposition vector which is a linear combination of computational basis states, alpha x, ket x, summation. Suppose I have such a vector. What is the probability? It should be, L2 norm should be, what is the L2 norm? Summation x mod alpha x square is the L2 norm. summation x mod alpha x square is the L2 norm. All of that should add up to 1. That is what is written as the L2 norm square. You see the 2 is L2 norm, square means square. So for any such superposition vector in our 2 to the n dimensional complex Hilbert, it's called Hilbert space. Okay. Complex Hilbert space, we write as a superposition. If it is a valid quantum state, it must have L2 norm 1. That's all. Yeah, so if it is, we are working in a 2 to the n dimensional Hilbert space. It is a vector space with inner product, because we are always going to have an inner product defined. So whenever we have a vector space with inner product defined, we call it a Hilbert space. So in the 2 to the n dimensional Hilbert space, we represent our quantum system, an n-qubit quantum system, as a vector which has L2 norm 1. Every quantum system will be represented with such a vector which has L2 norm 1, and every vector which has L2 norm 1 represents some quantum system. It is a one-to-one map. Okay? Okay? As far as what is known as pure states are concerned, there is also a concept of mixed states, but for quantum systems in this course, we will not get into mixed states because we will have a need of getting into mixed states. We are focusing here on algorithms. When we talk about quantum information, we will have to incorporate mixed states also, but because we are focusing here on algorithms, we will remain our focus on pure states. Pure states for us are represented by these vectors. This one you have to pass the mic.
Just putting together, just to make sure I got it. A state is L2 norm 1 if and only if it represents quantum states, because it works both the ways.
Yes, a vector, yes,
yeah,
is
okay.
L2 norm 1 if and only
if it represents quantum state.
Quantum state.
Okay.
L2 norm 1. L2 norm 1 or L2 norm square 1, it doesn't matter, it's the same thing. Because L2 norm, if it is L2 norm is 1, then square is also 1. It's a quantum state. Quantum state, a valid quantum, physical quantum state. Valid physical quantum. Like for example, when we said L1 norm 1 was representing for us a valid probability distribution. Correct? Probability distribution. A valid probability distribution, it must add up to 1. Similarly, a valid quantum state L2 norm must be 1. Any questions? Ket phi, yes. Ket phi is this addition. Addition, alpha x is complex numbers. Complex number times ket x. Ket x is a column vector. You multiply that alpha x by that column vector. Then you add all of them. That is your phi. It's a superposition state because we are taking it as a linear combination of basis states. That is why it's a superposition state.
Ktex, there is 2n dimensional.
2 to the n dimensional. 2 to the n. Remember what is happening here? N, for example, n here, so look, a string of n bits. Here what is n? Huh? What is n? What is n here?
6.
6. What is 2 to the n?
64.
This vector has how many entries?
64 entries.
So we are working in 2 to the n dimensional vector space. An n qubit system is a vector in 2 to the n dimensional vector space, not in n dimensional vector space. N qubit system, like 1 qubit system was in 2 dimensional vector space, 2 qubit system was in 4 dimensional vector space. Any questions? Mr. Superreddy. So I think next time onwards we might need one help to pass the mic, because all the participants are asking questions, right? So because we have to record, right, even their questions, so they have to have mic. It is better. So we might need somebody to help to pass the mic, because currently people are just passing like that. Maybe if there is a help, it's better. Yeah. Oh, you got it? Okay, so this transferring of the mic was not okay. Okay, so let's finish one last thing and then we can break for lunch. Okay. Actually, let's finish all this. Okay, maybe we'll take a little bit more, but let's finish all this. Okay. Okay, let me finish with this bracket notation. Okay, so we already saw the ket, right? So let's also see. Okay, so we saw this ket, right? Ket phi. Okay, what is ket phi? It's a column vector. The conjugate, the dagger of that is a row vector now. It is referred to as, okay, suppose this is phi, this is phi, this is psi. Okay, psi, bra psi. It's called bra psi. We'll see in a minute why it is called bra psi. That is the same as ket psi dagger, because this is ket psi dagger. Ket psi dagger is bra psi. Dagger we saw already is the conjugate transpose. Psi dagger. So ket psi dagger is bra psi dagger is ket psi, because you do dagger 2 times, you get back to the same thing. Column vector, you do dagger, you get row vector you do dagger, you get column vector. If it's a scalar complex number, dagger is what? Just alpha star, right? Because conjugate makes sense, but transpose brings you back to the same thing if it is a scalar. So alpha dagger is alpha star. A plus B dagger is A dagger plus B dagger. A plus B dagger is A dagger plus B dagger. That is the property, you can see. 2 matrices, A plus B dagger, A dagger plus B dagger. AB dagger is B dagger times A dagger. Oh, note the difference. It is not A dagger times B dagger. Because for matrix multiplication, the order matters. So it is B dagger times A dagger. Okay. Now you can see ket, I have ket theta, suppose. I write it as summation x alpha x ket x. What is going to be the dagger of this, which is the what we call ket theta, so bra theta. What is that? The dagger of the whole thing, right? Okay, you do dagger of the whole thing. I use these properties. What does it mean? This dagger can go inside the summation. Agreed? So I have summation x alpha x ket x dagger. What does this mean? Now dagger goes inside also, but it's a scalar alpha x. So alpha x multiplication any order doesn't matter. Alpha x star. Ket x becomes bra x. So this one will be simply summation x alpha x star bra x. Okay. This is how you can compactly do dagger and all that. So this is one thing. Another thing is, you can try on some examples. Maybe we will try it today, in the afternoon. Okay, now here example, ket psi is alpha beta, right? What is going to be bra psi? Dagger, right? Dagger meaning this will become alpha star beta star, row vector. Okay, ket phi gamma delta. Now inner product, one compact way of representing inner product is bra psi times ket phi. Bra psi times ket phi, but there are only two lines like this. You can make the two lines one line. Bracket. Why it is called? You see, now you will see the utility why it's called bracket. Bracket is what we say bracket, right? Bracket. Now you can see this one is like a bracket. Bracket here. So when you sort of append a bra with a cat and remove the two lines, make it one line, it becomes like a bracket. That's why they called it bracket. Also inner product, that is a scalar. But now that we have decomposed our bracket into a bra and a cat, we can even talk about ket bra. Ket bra now. So anyway, so this inner product was what? Bra psi was alpha star beta star times gamma delta, it becomes this. Now ket bra is now what? You see, bracket is a scalar, ket bra is matrix. Why? Ket bra, this is called the inner product, this is called the outer product. Outer product. Matrix. Why? You see, what is this? This is a column vector, this is a row vector. Now we are multiplying a column vector with a row vector. 2 cross 1 times 1 cross 2, 2 cross 2 becomes a matrix. Correct? So you can talk about bracket, you can also talk about ket bra.
I just have a very general question, like this is a shorthand
Yes.
of writing it.
Yes.
So when we are doing the calculation, is it?
Yes, exactly. Now we will actually see an example where all this shorthand is really helping us. We will see an example.
So we don't have to expand and then solve.
Exactly. Exactly. We'll see an example where all this shorthand is really helping us. Let's look at it here. Okay? Let's look at it here. Let's say I have this vector ket psi. 1 over square root of 2 ket 0 0 plus 1 over square root of ket 1 1. This is our vector. Clear? I want to do a transformation Hadamard tensor identity. Remember, it's a 2 qubit system. I am doing Hadamard on the first qubit, nothing on the second qubit. Represented as Hadamard tensor identity on the 2 qubit system. H tensor product I is a 4 by 4 matrix, you agree? It means what I am doing, remember, this is a 2 qubit system, psi. This means I am doing Hadamard operation on the first qubit and identity on the second qubit. Hadamard on the first qubit, identity on the second qubit. Doing yes. But identity in the second qubit means effectively I am doing nothing on the second qubit. Basically I am doing Hadamard on the first qubit. So what do I want to know what is going to be the resultant vector. One possibility is I just write what is Hadamard times identity. I write a 4 by 4 matrix. Another thing, I write psi as a 4 by 1 vector. I multiply, I see what happens. But that will involve this big calculation. Let us try to do it more compactly. What is it? Hadamard tensor identity 1 over square root 2. What is psi? This one is simply what? 1 over square root 2 ket 0 tensor ket 0 plus ket 1 tensor ket 1. Agreed? That is our notation. That means what? 1 over square root 2 comes out. Now Hadamard tensor identity multiplies. Remember the distributive property. Remember this is multiplication here. Hash tensor I multiplied with ket psi. So now this is the multiplication. Distributive property. Hash tensor I multiplies with 0 tensor 0 plus hash tensor I multiplied with 1 tensor 1. Agreed? Distributive property. Multiplication distributes over addition. Correct. Now, remember that property. A tensor B times C tensor D is AC tensor BD. So, H tensor I, 0 tensor 0 is the same as H times 0 tensor identity times 0. That property. Another thing, H tensor 1, sorry, H times 1 tensor H times, sorry, identity times 1. Agreed? Good. Now, hash times ket 0. He has done the calculation, right? Hash times 1 comma 0 was 1 over square root 2, 1 over square root 2. If you do hash times 1 comma 0, that is ket 0, 1 comma 0, you get the first column of the Hadamard matrix, which is 1 over square root 2, 1 over square root 2. Now that 1 over square root 2, 1 over square root 2 is the same as 1 over square root 2 ket 0 plus ket 1. Agreed? 1 over square root 1 is 1 over square root, take it out, 1 1. 1 1 is what? 1 0 plus 0 1. So that is the ket 0 plus ket 1. This 1 over square root 2 which comes out absorbs with this 1 over square root 2 becomes half. Same thing here. Hash times 1, remember now, it is the second column of the Hadamard matrix, which is 1 over square root 2 minus 1 over square root 2, which is 0 minus 1. The 1 over square root 2 comes out, absorbs here, half. Then identity to 0 does nothing. That is the same as 0. Identity to 1 does nothing. That is the same as 1. We got all this. Now you see, distributive property of the tensor over addition. So 0 0 1 0 0 1 minus 1 1. Agreed? So we got 0 0 1 0 0 1 minus, right, 1 1 1 minus 1. Mic to her.
Ket 1 1. Can we look at that equation and determine what will be the dimension of our answer?
This?
Yes. No,
Just
no,
this?
No, just this equation.
Which this one?
No, let psi equal to 1 by root 2 ket 0 0.
Yes.
By looking at it, can we determine what will be the dimension of H?
Yeah. You can determine. You see, what is this? This is a 4 by 1 vector.
Correct.
This is a 4 by 4 matrix.
Yes.
So 4 by 4 matrix into 4 by 1 is 4 by 1 vector. So dimension is not an issue. But what will be the vector? That either you can just multiply the whole thing and see, or you can do this more compact thing and you can reach here. The thing is that this more compact thing we will use a lot in going ahead when we will do circuit analysis. Okay? Because this helps us see, the operations, what they are happening in the basis states. Right? And then we just carry the addition, the linear combination, the superposition, we carry it forward. Or just repeat, what one? Oh, the whole thing you mean? This one? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. This one? There to next step. See, this is that property. A tensor C tensor C, sorry, A tensor B times C tensor D is the same as A times C tensor B times D. Correct? Okay? Any questions? So, I think today we successfully managed to finish till lecture 2. Okay, so we will now break for lunch. At 3 we will resume with tutorial. That time you can ask any questions related to the discussion that we had, and we will do some practice questions.
We are putting zeros and ones only, but
the superposition of zeros and ones also. Remember, we are looking at superposition states. So those are the states. Superposition of zeros, superposition of ket 0, ket 1, superposition of ket 0, 0, ket 0, 1, ket 1, 0, ket 1, 1, like that. Superposition states.
so that can be infinite, or that can be many, right?
Huh?
That superpositions can be many.
Can be many, exactly. Can be infinite, as you are saying, because you can take so many different linear combinations.
So all these states will be described as a linear combination of base states. Right?
Exactly. All these states will be described as linear combination of basis states. Okay? All right. So, okay, so this is some information we have already discussed, but here it is again written. A square matrix is stochastic if and only if all its entries are non-negative reals and the entries of each of its columns sums to 1. Right? We have already seen this one. A square matrix U is unitary if and only if satisfies U times U dagger equal to identity, where U dagger is the conjugate transpose of U, I is the identity matrix, and dot denotes matrix multiplication. For two column vectors V and U, their inner product is defined as this thing here. The LP norm, see, we have seen the L1 norm and the L2 norm. Okay, in general, you can define LP norm. LP norm of a vector V, V1 up to Vn transpose. So this is a column vector written as a row vector transpose. in a complex n-dimensional Hilbert vector space is given by the P norm of V, LP norm is V1 to mod V1 to the P plus mod V2 to the P all the way mod Vn to the P whole to the 1 over P, correct? That is the LP norm. Then a set V1 to Vn is called orthonormal if each vector has L2 norm 1 and the inner products of distinct vectors are 0. So pairwise inner products are all 0. That entire set is called orthonormal set. Each vector has L2 norm 1 and all the pairwise inner products are 0. This also I will provide to you, okay, don't worry. Singular value decomposition, okay, this is a new thing. For every matrix A, there is a thing called its singular value decomposition. For every n cross n complex matrix A of rank A equal to R less than equal to n, there exists unique positive reals S1, S2 up to SR and orthonormal sets V1 to VR, W1 to WR such that A is written as summation I1 to R SI times WI dot VI dagger. That is, the numbers S1 to SR are called singular values and the set of vectors V1 through VR and W1 to WR are called right and left singular vectors respectively. So, what is happening? You have a matrix A, you can always write it in this form. This form is called as the singular value decomposition. Singular value decomposition. What does it mean? You take it as a sum. SIs are singular values which are positive reals. If A has rank R, then 1 through R, SIs are positive reals. WIs are what are known as left singular vectors. Left singular vectors. VIs are called as right singular vectors. All the W1 through WR together form a orthonormal set. We know already what is a orthonormal set. The V1 to VR together form a orthonormal set. And this one WI times VI dagger. WI is a column vector, VI dagger is a row vector. So WI times VI dagger is a matrix. So this is a matrix, this is a scalar, SI. In fact, a positive real, not even complex. SIs are singular values are positive real values. You multiply all these and you add it up, that is what your matrix will be. So every matrix A has such a singular value decomposition. Agreed? Very good. Now let us get to our questions. Okay, first question. The Pauli matrices are given by, these are known as Pauli matrices, okay, named after physicist Wolfgang Pauli. So, Pauli matrices, identity sigma x, sigma y, sigma z. Verify that all 4 matrices are unitary. Okay. So now I need a volunteer who will help us verify that all of these matrices are unitary. Who will be happy to do that? Please raise hand. Anybody? Yes? This should not be difficult, right? So anybody wanting to do that? Yes? Okay, in order to give incentive for people to come here, let us do like that. Each time a person comes here, doesn't matter, they give right answer, wrong answer, doesn't matter. They get 1 point. Okay? Then all these points we add and at the end when we do the assessment, we add these points and that adds as bonus for your assessment. How about that? Oh, now we already get one hand. Fantastic. Please come. Yes. Somebody has to record. If any person is coming, record their name and that's it. Just we do +1 in front of their name because they volunteer to come. Now we have to, we had this thing, no? One mic we have. Here. If you are speaking, you can use this mic. Maybe we need light here. That works. Is it visible? What he's writing? Maybe you do like this. 1 minute. 1 minute. Better, right? Can you please explain?
Okay, we are given 4 poly matrices, identity X, Y and Z. So we need to prove the 4 poly matrices are unitary. For unitary, the condition is like U times U dagger is identity. So for identity matrix, we do its dagger operator. So dagger is defined as complex transpose. So when we do this, this is a real value, so there is no need of this conjugating. So we just transpose this matrix, we will get the same matrix. So by multiplying this I and I dagger.
When he is explaining, if you have any question, please you can ask the question. Okay, when he is explaining.
So by multiplying these both, we will get identity matrix. So because we multiplied I and I dagger, we got identity, so it is unitary. Similarly for poly X gate, we do the dagger operator. So these all 4 entities are real values, so hence no need of conjugating it. So we just do the transpose and multiply with the original X. So we will get identity. So hence this is identity. So X and X dagger is a poly X is the unitary operation, unitary matrix. And similarly for Y, here Y has complex values. So we need to conjugate it. By conjugating it, this minus I becomes plus I and plus I becomes minus I, and then transposing it will give the same Y matrix. So by multiplying both of this, we get I. So hence Y is a unitary matrix. And similarly for Z, Z also has a real values. So no need of conjugating it, and we transpose it. So we will get the original Z, and by multiplying Z times Z dagger, will give identity. So this Z is also a unitary matrix. Hence identity, poly X, poly Y and poly Z are unitary matrices.
Okay, clear? How he is proving unitary? Simply he is calculating for every matrix he wants to show it is unitary, he calculates the dagger, then multiplies and shows that the product is identity. Once he has shown that, that is enough. Okay, agreed? Very good. Now here next question. Verify that the following set of vectors is orthonormal. Verify that the following set of vectors is orthonormal. Okay, how we are going to do this? Anybody? Anybody? Yes? Any volunteer? What about, yeah, you are coming? What about normal? Can you at least verify that they are all normal? L2 norm is 1. You can try to verify that. Anybody can try to verify that. They can also come. Just normal. L2 norm is 1. Yes. Just for V1, what is the norm for V1? Yes, please come. You can erase that and you can write it there. Okay, can you explain? You can use the mic here, the mic.
So it's a I'm using here the property of tensor product. So it's a scalar 3 by 5. We can take outside that tensor product. So we can do tensor product of two vector, which is this 1 0 0 and 4 and 5 is a scalar. We can take out by the property of tensor product. Then using that two vector, we'll get this vector. Then again, using that normalization, L2 normalization, which is then alpha square plus beta square. So because of that, 9 by 25 and 4 by 16 by 25.
Clear? Any question? Any question about this?
Same thing for
Yeah, same thing. Maybe you do for V3, V4 you do because they involve complex numbers. You can erase the other things and do it. Oh, you can erase all. No. There, up. Yes. V3. No, V3, that one you have to be careful what you write there. No, I'm saying just the thing that you wrote 0101. Yeah. No, you should write, don't write equal to, write mod V, write L2 norm, like this you write, I tell you. See, if you write equal to like this, then equal to like this, people will think this is equal to this. Okay? What you have to write? Norm V1 2. Okay? What you write now? 4 over 5 and 1 by 5. Yes. Can you explain why it's like that? But the I will not matter. Yes. Remember, you're doing not the complex numbers. I mean, you're not doing that complex number square. You're doing mod square. So I over square root 5, the mod is 1 over square root 5. That one you're squaring. Okay. If you just do I square, it will be minus. Then it will be confusing. Okay. That's why it's like that. Now it is 1. Any question? Any question about this? Anybody has a question? Okay, now can you just do the inner product of V1 and V2? Just do the inner product of V1 and V2. Yeah, can you? Or it's okay? Just try, doesn't matter. Try. V2. Yes. Or you can do V1 and V3 because you have already written V1 and V3. You can just do. No. When you are doing V1 and V3 is okay, but inner product you are doing. Remember that. How do you write the inner product? Correct. V1 dagger multiplied with V3. Okay. Yeah, you can do that. Just is the pen okay, or is it you want to another pen? Is pen okay? Is 0? Can you explain? Please explain. No, no, take the mic.
We have V1 this, so we just simply add this two vectors. So which is nothing but 3 by 5, 0, 0 and 4 by 5. Similarly, B3 is this vector. We just add this two vector, which is this. And since it is an inner product, so I'm using here transpose because all number in real number. So V1 transpose dot V3, which is column vector and the row vector, and which is simply but 0. So that means two vectors are orthogonal to each other.
Yes, whenever a set of vectors is orthonormal, you have to show that each vector L2 norm is 1 and every pair is orthogonal. That is, the inner product of every pair is 0.
Yes. When we form a matrix with this vector, it's a unitary matrix.
That is also true. If you form a matrix with these vectors as the columns, then it's a unitary matrix. Okay, now what we are going to do is, you are doing this calculation by expanding all the vectors, right? Now let us try to do it in the Dirac form more compactly. Okay, so maybe you just erase everything. Okay, erase everything.
V1 dagger, V3 and V3 dagger, V1, they are different values.
Yes.
So we have to calculate them separately, like I am saying V1 is orthonormal with V2, then V2 with respect to V1 has to show.
No, because you see, remember one thing we noted, inner product of V1 and V2 is the conjugate of, because inner product is a complex number. If you take its conjugate, you get the inner product between V2 and V1. Okay, inner product between V1 and V2 is equal to inner product of V2 and V1 conjugate, simply conjugate. So if 1 is 0, conjugate of 0 is 0. So you don't have to calculate, it will still be 0. Okay. Wait. Okay, good, fantastic. Yes, good. So now she is writing all these vectors in the Dirac notation. Agreed? Good. Now when things are in the Dirac notation, it is much easier to show, okay, about orthonormality. This is in Dirac notation. Now let us do the following. Okay, remember during the lectures we said one thing. No, wait, what do I mean? Remember that during the lectures we said one thing. Suppose I have any n bit string and I have alpha x ket x. What was the, what we wrote was the L2 norm square of psi. What did we write it as? Remember in the lectures? If I express any vector in this notation, look, she has expressed V1 like this, right? Alpha x ket x, 2 over 5 ket 0 0, 4 over 5 ket 1 1. Agreed? It is the same as this notation. In this case, in her case, n is 2. X is a string of length 2, 0 and 1, 0 0 1 1, 0 0 1 1, 0 1 1 0, 0 1 1 0. Correct? It is in this form. Agreed? When it is in this form, what was the, how we wrote the L2 norm here was, remember in the lecture? Exactly. We wrote summation over x mod alpha x square. We wrote that, remember? So what is the thing now? Now what is the thing? If you use this formula, what will be the mod? What will be the L2 norm square? No, 4 by 25 plus what? Sorry, it's 3. It's 3, right? Okay, 9 plus 16. Here also, okay. Here 4 plus 1, 5. So you can see that if you use this formula, very easy, you don't have to do tensor nothing to show it is normal. Now in a product, okay, suppose I have phi, okay, which is summation x beta x x, okay. Now can you do the inner product of, can you tell me what is this? No, you just do it in this form. Suppose psi is given like this, phi is given like this. What is the inner product of psi with phi? You just write what is bra psi. First write what is bra psi. Write bra psi here. Here you write bra psi. What is bra psi? Ket psi is this. Write bra psi there. Very good. You see this? How she wrote? Bra psi. This is what we saw, right, also in the lecture. Now you multiply bra psi with ket phi. Multiply now. No, don't directly do it. Do it one. Just do systematic one by one. No. Write that one first. Write that one. You can take the eraser. I think you have the eraser there. Here, you can use this if you want. Here. Want to use this? Write that one first. Just write, you see, you are multiplying two things. You are multiplying this with this. So write this first, then write this first, second. Put the bracket. See, when you are multiplying, no. Look, here one bracket, here another bracket. See, when you are multiplying, and if this is already a sum, you should keep the sum in the bracket. Then another thing, when you have summation over x here, also summation over x here, you should use a different letter, because if you are using x and x, it's confusing. Here you use y. Okay, whenever you have sum of terms multiplied with sum of terms, if you are using some letter for this, you should use a different letter for this, otherwise it's confusing. Okay, now you multiply. How will the multiplication happen? Yes, now you see this? Now you see this one? Agreed? Now, if x is different from y, what is the inner product? Huh? Why is it 0? Whenever x is different from y, inner product is 0. Why it is 0? Huh? Huh? No. Forget alpha x beta y. Simply what is bra x times ket y? If x is different from y, what is bra x times ket y? 0. Why is it 0? Huh? Huh? They are orthogonal to each other. Not orthogonal. Okay. Okay. Let's do like this. Where do I write? Here. Okay. What is inner product of 0 with 1? What is the inner product of 0 with 1? No, you simply tell me what is the inner product. Why is it 0? Can you do the calculation and show it is 0? Right, bra 0 she wrote as that row 1 0, and ket 1 she wrote 0 1, and multiplication turns out to be 0. So we see inner product of 0 with 1 is 0. Okay. Now what is the inner product of 0 0 or let us say, I do not know, 0 1 with 1 0, what is that? Right there only, or you could do it like this. Okay, let's erase this actually. We'll come back to this question later. Let's do this first. What is the inner product of, you can do the calculation here if you want. Okay, let me give you a simpler one. 0 0 with 1 0. Okay, what is this? 0 0 with 1 0. Yes. Very good. Very good. See what she did. She is now using this compact notation. No, no, it's very good, very good. So you see, 0, 0 is 0 tensor 0. Agreed? 1, 0 is 1 tensor 0. Agreed? Now she used that formula. A tensor B multiplied by C tensor D is AC tensor BD. So she multiplied like this. 0, bra 0, ket 1 here. Tensor 0, 0. She wrote. Why you are writing so much now? No, 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 that's it. Okay, remember the formula. A tensor B, C tensor D, AC tensor BD. So this is A, this is B, this is C, this is D. AC tensor BD. Agreed? She used this formula. Now what happens? What is this inner product? 0. Tensor, okay, fine, tensor. What is this inner product? 1. Because now it is the L2 norm. Inner product of a vector with itself is the L2 norm square. So this is 1. But these are scalars. Tensor product of scalars is what? Just the product, regular product. You can see it. Tensor product of scalar by definition would turn out to be just the regular product. So this is equal to 0 times 1. What is this? Agree? Now I give you something more general, okay? What is the general? I give you this string x. It's a n bit string. So what does it become? x1 tensor, x2 tensor all the way to xn. Agreed? Where each of the x1, x2, x3 are the individual bits of x. X is the n bit string. Okay? X is a n bit string. Here 1 0 is a 2 bit string. 0 0 is a 2 bit string. Like this x is a n bit string. Individual bits are x1, x2 up to xn. Agreed? But how we write 1 0? 1 ket 1 tensor ket 0. So it becomes ket x1 tensor ket x2 tensor all the way to ket xn. Agreed? That is our representation. Now I give you another y, which is y1 tensor y2 all the way up to yn. Agreed? Now what is going to be inner product? You write that one. You write there only, or you can write below, or you can erase this and write also here. Yes, very good. Use this formula. You can use this formula here. No, here, that one. No, this one, middle one. No, middle, ABCD. Yeah. Use that formula. No, you write bra x first. Don't jump the steps. If you jump the steps, you will get confused. Write bra x first. Yes, very good. Yes. Yes. Then put bracket, very good. Now, yes, yes, very good. Yes, very good. Now that is equal to, use the formula now. Yes, very good. Very good. Very good. Now you see this? Now you see this? Now if x and y are different, at some location they will be different. At some I, xi will be different from yi. That time what will be the inner product? Xi yi? 0, correct? We just now saw. Anytime the bits are different, the inner product is different, 0. So that will be 0. Now everything else multiplied with 0. So even if one place it becomes 0, the whole thing becomes 0. Agreed? So anytime you have x and y are different strings, the inner product is, and if they are the same string, the inner product is clear? Clear this one? Now you do this in that notation. Now remember you were doing all this in the continue here now, continue here, continue here. Now we got right, that if x and y are different, inner product is 0. So what will happen here now? Whenever x and y are different, 0. So now it will become what? No, that's okay. But you just write, simplify the summation now. Simplify the summation. There are two summation, right? Yes. Okay, but now can you further simplify? See, if x and y are different, it's 0. So do you have to can't you simplify it? So now if x is different from y, this is 0. So just do a summation only over x. Correct? Only over x. Alpha x star, beta x, and inner product of x with x. See? Because whenever x is different from y, this is 0. Gone. Only things left are x equal to y. X equal to y is left. So you just retain those ones, x equal to y. Correct? Now it is inner product of x with y. What is this? Summation x, alpha x star, beta x. That's all. Because this is 1. Inner product of x itself is 1. So this is it. So whenever you have, so what did we get here? Agreed? Yes? If psi is written like this and phi is written like this, then the inner product is, agreed? Similarly, if I want to write the inner product with phi with psi, it is beta x star alpha x. Agreed? Yes? So, in fact, you can also see that inner product of psi with phi is this number, right? Alpha x star beta x. Correct? If I do the whole thing star, which is this whole thing star, what do I get? Can you write this? Write this. Beta x. Correct? What is this equal to? So this answers your question? Yes? Excuse me? See, this answers your question. You were asking what is the relationship between inner product of psi with phi and phi with psi. So psi with phi star is phi with psi. Correct? Agreed? So, see, but the point is this, whenever you write ket psi in this form, in this direct form, ket phi in this direct form, then the inner product is very easy. You don't have to expand x in the vector, this, that, nothing. Simply do summation x alpha x star beta x. You see this? Agreed? Now let us do like this. Okay. Now you write all these vectors in the denotation and use this formula for inner product. No, don't write V4, just do okay, you just do V1, V2 first. Inner product of V1, V2. Use the formula. V1 and V2, 3 over 5, 4 over 5, 4 over 5, 3 over 5. Can you explain it to them now? Just explain. Use the mic.
So this is my V1 in terms of Dirac notation. So if I use this formula, which is nothing but transpose of this scalar into this, and this is in real numbers, so which is nothing but we can do direct product of this scalar, which is 12 by 5, and there is a minus because it's a summation of this thing, so I can do plus minus and this term.
Okay, very good. Now you do V1 with V3. Use the formula V1 with V3. V1 and V3, what you are using? That formula. How you are using that formula? Yes, so how do you do that? How do you do that? What are you doing? What are you supposed to multiply? Coefficients of what with what? What are the coefficients? Huh? That is 3 over 5 is the quotient of what? No, I am asking you 3 over 5, 3 over in V1, 3 over 5 is the coefficient of what? Hmm? No, you do it slowly, huh? Don't do fast. If you do fast, then you will make mistake. No, don't do like that. I said we have to use the formula. Again, you are doing your, then it will be your elaborate method, right? You can use this. You can use the eraser here. Use the formula. Simply use the formula. We have a formula. Agreed? So simply, let us simply use the formula. What is our formula telling us? What we are supposed to do? Don't look there. Look at there. The formula is there. What is the formula? Just read out the formula. Read out. Alpha x. That is what it is, right? Let's simply use the formula. Why you get confused? That is not a problem. See what it is telling us, alpha x is the coefficient of x. Beta x is the coefficient of x. So take the coefficient of 0, 0. What is the coefficient of 0, 0 in V1? What is the coefficient of 0, 0 in V3? What is the coefficient of 0, 0? Yes. No, don't jump the step, write it. Write the coefficient, multiply the coefficient. Multiply with 0. Correct. Now plus coefficient of 0, 1. What is the coefficient of 0, 1? 1, 1. Okay, 1, 1 you did. Fine. 1, 1 is 0 plus coefficient of 0, 1. What you are doing now? What is 3 over 2 over square root 5? That is the coefficient 0, 1. Yeah. Times. 0. Coefficient of 0. What is the coefficient of 0, 1 in V1? 0. Correct. What is the coefficient of 0, 1 in V3? Okay. Plus coefficient of 1. Yes. You see this now? That is where we are using the formula. Simply for every string x, we are multiplying alpha x, beta x star, or alpha x star, beta x. That's what we have to do. Now here 3 over 5, 0, 4 over 5, 0, 0, 2 over square root 5, 0, I over square root 5. Multiply like this. Now what is the addition of this? 0. Correct. So this is a more compact way of seeing this. V1, V3 we saw. What is V2, V3 now you do? Now you see that? Yes, you have a question. Can you please pass the mic to her? Here.
So I just had a so that xy equation we have in the end over there. If we just represent it as a Kronecker delta function, we'll eliminate all of the solving procedure, right?
Which equation?
The alpha star beta y x, bra x and ket y. Before we substitute y equal to x.
Yes.
Then we can eliminate the solving also if x and y are different. It's just automatically 0 if you write it as a delta function.
No, that's what we did already. Because we removed all terms with x different from y.
Yeah.
But we have to retain the terms where x equal to y, no? That's what we did. Alpha x star beta. That's what we did. We already put the Kronecker delta there. But now you can see this. So now all the pairwise inner products are 0. Okay. Yes, you want to say something? Maybe you want to explain. Just explain this. Explain the V1 dagger V3 inner product, and also the V2 dagger. Oh, you should speak in the mic. Always speak in the mic. Can you just say it again on the mic? Huh? No? Why you don't want to say it? No. That's the whole point. We don't want to do it with matrix. We want to do it in the compact notation. Because later the compact notation will help us. You see, she did it initially by matrix. But we want to do it in the compact notation. Huh? She is able to, yes. But is it clear, this one, or no? Any question you have? Anybody? Huh? Clear? You explain. He asked you to explain. Take the mic. Take the mic. No, you can explain. Not a problem.
This is the formula. This is a product of inner product of two different vectors states. So which is given as this. So that means with each string we have to multiply. So means we have to multiply only the scalars. So here, firstly, what I'm doing mistake is multiplying this two, which is not possible because the formula is with the same this state we have to multiply. So since is a 0 0 and 1 1, so here it is 0 1 and 1 0. So the another two states, it's a 1 0 0 1. So which are here 0 0, and since it is not there, so we multiply this two by the formula this and this, which is a direct as a multiplication of the scalar term, which is 3 by 5 and 0. So for here 1 1, so which is here 0. So only this scalar term by this formula. So in 1 0, it's a 1 0. So this term, and here 0 1, and here 0. So it's a direct formula, the scalar will make. But if you multiply these two, which is by this formula, we'll get direct 0 as sir said here.
Clear? Any question? If you have any question, please ask. Yes? Is it clear? Yes or no? Raise hands to whom it is clear. Raise hands to whom it is not clear. Not clear to you. What is the question? Completely not clear. Okay. But thankfully this is all being recorded. Okay. So what you can do is, maybe you can go back home and look at the recording, and if it is not clear tomorrow also, then you can ask. Okay. Are you able to say which part is not clear, or like many things are not clear here? Okay, sure, no problem. Then you go back and look at the videos and try to see if you can put your finger on what particular thing is unclear, then that we can try to discuss tomorrow. Okay? You can also try asking your friends later on. Okay? So as I said, in the meanwhile, when you get these kind of breaks in the evening, you can try to brush up little bit on your knowledge of linear algebra, so that all this discussion becomes clearer to you. Okay? Agreed? Okay, fantastic. So we are done with the time now. So we stop here. We will be discussing some questions, and for those questions, for some of them we will also be providing the solutions. Maybe some questions we are not able to discuss, for them also we will provide solutions depending on that. You can go through the solutions at your own pace later on. Okay? This yes, we will share all this. Okay? Okay, thank you very much. So what we are doing, I think, is noting, right? For her also we can note and give her, for her we can give, she should get at least okay, not 5 but 2, we give her 2 points. No, you solved one question only. Yes, yes, okay. So I think you are noting, is it, or you just, you know the name, like, so you just give 2 points to her. Okay? All right, thank you very much. We resume tomorrow. So by the way, is this timing working out for you guys? Lectures 11 to 1 and then break for lunch and then 3 to 4, working out? Or you want to shift this one to 4 to 5, like that? You want more break in between? This is okay?